Okay, so in this video, we will be talking about, we're just starting chapter 14, repeated games, where actually the only repeated game in chapter 14 that is considered is the prisoner's dilemma. Which looks like this. Got 2, 0, 0. Yes, we'd like to be able to sustain 2, 2 instead of 0, 0. But for player 1 there is this deviation, and for player 2 there is this deviation. Yeah. It's better if I have a 1 and 1 here. Because otherwise this becomes it's a weak Nash equilibrium otherwise. So, prisoner's dilemma. The usual idea is that D is strictly dominant instead of C. To deviate or is better than to cooperate, right? Because if player 2 plays C, player 1's best response is to play D. If player 2 plays D, player 1's best response is to play D. If player 1 plays C, player 2's best response is to play D. If player 1 plays D, player 2's best response is to play D. And so DD, defect, or deviate is the only outcome of the game when you play it once. But what happens if you can play this game an infinite number of times? If this game is to continue and happen an infinite number of times, then these two players could just get together and come up with a strategy to cooperate. In fact, they don't even need to get together. I mean, imagine player 1 playing a strategy, it's called a grim trigger strategy, where player 1 just says, as long as player 2 cooperates, I'm going to cooperate. And player 2, on the other hand, makes the same sort of strategy up in her head. And if they play that strategy where, unless either one of them has ever defected, has ever not cooperated, that they cooperate, they can actually sustain cooperation as an equilibrium strategy, as an equilibrium outcome. Okay. Which leads naturally to a few questions. One is, do they need to have some amount of patience in order to be able to sustain it? Two is, do they need to have this whole idea of never cooperating again with a person if that person defects once is a bit strict. I mean, think back to your own friendships and relationships. You don't do that. I hope you don't do that, because that is a bit strict. And so, can you sustain cooperation with limited punishment, with only limited periods of punishment? Other questions that naturally arise are, well, we've shown that CC is now an equilibrium outcome, but can we also sustain other outcomes? Could we sustain CD, for instance? Is it possible even? What else? Yeah, also, the things we learn in chapter 14 are things that will apply to other games as well, not just Prisoner's Dilemma. And so chapter 15 explores it, which we will try to get to, but we might not be able to get to chapter 15. So I do recommend that if we don't get to chapter 15, that you take a look at it. Now, the first thing we need in order to be able to do repeated games is we have to figure out payoffs, and payoffs for those repeated games. So, our payoff will be discounted. Think of delta, which is some number between 0 and 1, as your discount factor. A discount factor tells you the ratio between the value of $1 in the next period to now. The assumption that economists make is that $1 1 period from now is going to be worth less than $1 right now. It works in finance very easily because a year from now, $1 will be worth $1 plus whatever interest rate is going on in the market. Typically in the US, it's around 2% plus minus something. I don't know what it is currently. It's probably lower than 2%. But yeah, money now is better. And so we typically, when we work with deltas, we'll typically be thinking about some number that's something like 0.9 plus minus something. Okay, your payoff will be what you'll get in this period based off of the action profile of all of the players, plus delta times what you'll get in the next period. Utility, say of player I. This is payoff for player I. Delta squared times. This is not a to the power 1, a to the power 2. This is just the action profile chosen in the first period, action profile chosen in the second period, action profile chosen in the third period, and so on. Another way to write this function is to have the sum of t equals 1 to infinity delta to the power t minus 1 u of I a t. Put it in superscript just because that's the way the book does it. I actually prefer it in subscript because otherwise it looks like a power. But okay, I'll do what the book does and put that in the superscript. Okay, so that is your discounted utility. This also works for lotteries. So in the case of a lottery, you'll just have the utility that you would get from that lottery over here. So if instead of A, you have alphas, if you have a mixed strategy, then you just calculate the expected utility of that mixed strategy for that period and discount it. So this works perfectly well with mixed strategies as well. Another thing, another concept that you need to know about is called the average discounting. The discounted average. The idea behind the discounted average is this. You could have several streams of payments. Let's say that stream looks like W1, W2, W3, just some different numbers. You'll put delta here, delta squared here, and so on, to get what your utility is. But could you also represent this with some constant? Right? Is this also equal to some constant that is C plus delta C plus delta squared C, and so on? So for instance, just to throw some numbers out, let's say that discounted stream looks like you get $100 right now, $150 later, $50 in the third period, and so on. It just keeps varying up and down. Is there some constant number that you could get, something like 95 for instance, which is equivalent to that crazy string? And what we find is that that constant number, so this infinite sequence equals C divided by 1 minus delta. It's just the sum of an infinite geometric sequence. If you don't know what that means, Google it. Not going over that. It's an infinite sum of geometric sequence, or the sum of an infinite geometric sequence. And let's say this is ui. So that little c will just be 1 minus delta times ui. And so basically what you're trying to maximize could be this, but because 1 minus delta is just some positive number, it's equivalent to maximizing that constant as well. So when we're defining the game and we're figuring out what the agents within that game are maximizing, we sometimes just look at the discounted average, which is this C, rather than the actual payoff, which is this UI. It's equivalent because the book does it either way. I mean, the book sometimes does the discounted average and sometimes will do this UI. I had to mention it. In actual papers and research, when we write, we pick one at the beginning of a paper and we just keep working with that one till the end of the paper. So, okay. So, see you in the next video.